All right, so in section 19.1, we talked about acids and bases. We introduced their really simple properties, and we also introduced three models of the way that we could classify an acid or a base. We talked about the Arrhenius model, which did not include a whole lot of substances, because to be an acid, you had to have that H. To be a base, you had to have that OH, okay? Then we got into our Bronsted-Lowry acids and bases, and a Bronsted-Lowry acid and base is a lot more inclusive, because a acid is considered an H plus donor, a hydrogen ion donor, and a base is considered a hydrogen ion acceptor. A lot more substances could be classified as Arrhenius acids and bases, and it's actually one of the main methods that we use in chemistry to classify if something's acid or base. There's still a few things that couldn't be classified as either an Arrhenius or a Bronsted-Lowry acid or base, and so we talked about a Lewis acid and base, and that was an acid is an electron pair acceptor versus a base is an electron pair donor. Now we get into our strengths of acids. We have strong acids, we have weak acids. We have strong bases, and we have weak bases. So we start out here with strong acids. They say that these things ionize completely, all right? This means 100% of these H's that you see on any of these 7 strong acids will break away from their other negatively charged anion. Now, I hate to do this, but there's only really one way to do this, and you have to memorize the 7 strong acids, okay? So as you write these notes down, make sure you remember, hey, I'm going to have to remember these 7 strong acids, okay? Because based on that is going to affect our properties, and eventually we'll see affect our calculations later in this chapter, okay? So put a star, highlight. That's why I had you write these down. They are very important, okay? A strong acid, like we said here, it says it ionizes completely. Okay, what's the so what for this? The so what for this, if I gave you a chemical reaction, I said, hey, this is an acid-base reaction, tell me if it's strong or weak. What you would be looking for is this arrow. You want to see a single-sided arrow. What that means is that 100% of this H, 100% of that H is going to break away from the Cl, okay? And 100% of those H pluses get donated to H2O, and we have, again, most important thing, a one single arrow as our acid, okay? Or as our strong acid shows. Now, the conjugate base, which if we just highlight, I'll take a different color here. This right here, Cl minus, is our conjugate base. That is very, very weak, okay? Key thing is this. A strong acid or a strong base is going to have a single one-sided arrow, meaning there is no reverse reaction like we saw with equilibrium. Now, we're going to talk about how that can be different, but a strong acid, single arrow, what that means, it's 100% ionized, okay? A weak acid. We talked about strong, now we talked about weak. Now, remember, an acid, and in our class, we're going to say this. We're going to keep the Bronsted-Lowry acid and base definition, and our Bronsted-Lowry acid base says an acid is an H plus donor, a base is an H plus acceptor, okay? They only partially ionize. So check this out. On the right-hand side, it says weak acids. If we take a look here, those arrows right in the middle of that very far right-hand side, those arrows, they are all equilibrium arrows, meaning they only partially ionize. Equilibrium arrows only partially ionize. Now let's go a little bit further with this. If we have our equilibrium arrows, we can utilize that information that we learned with equilibrium, where we talked about big giant K, and we use a little a to represent our acid, all right? Now, typically, when we say they only partially ionize, typically only 5% of those H's actually break off, and they're actually donated, in this case, in our class, to our water, because we're dealing with our aqueous solutions. So these numbers, you can see 8.9 times 10 to the negative 8th, pretty small number. We go all the way down, 4.7 times 10 to the negative 11th, even smaller number. If something's less than 1, our reactants are going to be dominant, meaning there's a lot higher concentration of reactants than there is products, okay? So keep in mind when we talk about products and reactants dominating the equilibrium, it is saying, okay, if it is the case, reactants dominate, very little of those H's actually broke off of that original acid, all right? So our weak acids here, all right, forward and reverse reactions are going to occur, and they're going to occur at particular equal rates, all right? Now, we talk about this, okay? We have our equilibrium expression, and the first thing that I would like you to do is identify, hey, this is a weak acid. Well, we know that because there is equilibrium arrows. Then the second thing that we should do when we get to these types of problems is write our Ka expression. Now, big giant K, and big giant K is always going to have products on top, and we only write our aqueous, and our aqueous and our gases there. So the only thing we're going to have on top here is H3O plus, and remember brackets mean concentration, times the conjugate base here, C2H3O2, all divided by, the only thing that we're going to put on bottom is that acetic acid. Remember, H2O is a liquid, it's a pure substance, so we're not going to put that in our equilibrium expression. Okay, so that's how we write our Ka. All right, that's an important takeaway that we have here. All right, only about 5% of this H that I'm highlighting right now breaks away from that original acetic acid. Now, on the flip side, we talked about acids. Now we can talk about bases. Again, the easiest way to remember this, our strongs, you are going to have to memorize. Now, strong bases dissociate completely. Again, I want to take a look here on this chart. All of these arrows are one-sided single arrows. It's an important detail that we notice this. And again, the only way that you will know these is memorize the strong base list. Notice all of them have OH hydroxide. They all have to have that hydroxide ion to be considered a strong base. Okay, so memorize this list. Star, highlight, underline, do what you need to do there. Okay, strong bases. Again, key giveaway is going to be that one-sided arrow that's going to say, all right, these things ionize completely, meaning 100% of that sodium is going to break away from that hydroxide. Okay, that is considered a strong base, and that's what we consider to be ionized. Okay, again, you have to memorize that list to know what is a strong base from what is a weak base. Okay, weak base, they're not going to have that OH minus, but they are going to accept, that H plus, but they're only going to partially accept this. Again, just like I pointed out with our acids, notice here with weak bases, equilibrium arrows. Equilibrium is going to come back into place. Now, our Kb, the reason we use B here is to indicate base. Equilibrium, we reintroduce that big giant K. And once again, I'm going to say, hey, Kb is less than 1, which all weak bases are less than 1. our reactants are going to dominate. And then that key thing here, less than 5% ionizes. Okay, so we end here. I just want to write the Kb expression here. Remember, forward and reverse reactions are occurring. And so if we wrote the Kb expression, 1, we know we have to do that because of these equilibrium arrows. 2, we identify this. NH3 is actually considered a weak base. And so we would say, all right, we need to write down our Kb, which equals our reactants. Remember, we're only putting aqueous and gases. We don't have to worry about gases. NH4 times our OH minus, all divided by our only NH3, and that would be our Kb expression. All right. We're going to use this information to talk about pH and do some more in-depth calculations with section 3 and 4 of this chapter.